Alright, time for another video update on the Janus project. If you've been following the blog at all that I have on buildlog.net, you can see that what I've been working on lately is having a hardware integrator. And you can see I've built a rather scrappy looking test circuit board, but it does work, and it works well. These are 4-bit up-down counters. I have 5 of them for the x-axis and 4 of them underneath the ribbon cable here for the y-axis. Essentially what it does is it listens to the smooth stepper. Smooth stepper communicates to the motor driver through this ribbon cable. Basically it's a 25-pin parallel port connector. So what I did, I got an insulation displacement connector and just put it right in the ribbon cable. That was the cheapest way to listen into the signals. And what it does, it listens for X and Y pulses as well as direction, and the limit switches on X and Y, so it resets the counters. And that all that information gets communicated to a microcontroller through this ribbon cable. And that's connected to an Arduino Mega right now. It's just hanging here, but if you saw the last group of pictures, I have some studs here that it's going to sit on when it's done. So anyway, it looks a little ugly on there too, because I found out that the ports on the Mega aren't exactly all close and connected. But that's okay. It still works well. So that's connected into my control computer, and right now I've got the code up there. Very, very simple. I wired it in so that you would just be reading five digital ports there, and you get all the information that you need. Now on the new Arduino Duo, D-U-E, I don't know how you say that, but that's going to be a 16-bit or 32-bit microcontroller, but it's got groups of 16 pins per port rather than 8, so it'll take fewer machine instructions to read them. It'll take a total of 3 to read the pins on that one, and whereas right now it takes 1, 2, 3, 4, 5, it takes 6, at least 6 machine instructions to read that. The digital read probably counts for about 8 on there. So I don't know, I'm going to have to figure out a little bit faster way to do this, but this works, and it works well. So the advantage of having such a hardware integrated system like that is that I will be guaranteed never to lose a step. That smooth stepper can produce pulses at 2 megahertz frequencies, which at 16x microstepping, which I have on this machine, that amounts to about 70 meters a minute travel. So there's a potential there for very, very high speed counting and integration if I could get a higher speed microcontroller. Again, at those kind of speeds, our 40-watt laser wouldn't produce very much burn, but in the material, but it's at least under development here. So so right now you see it's printing out to the screen the actual pulse pulse counts on the X and Y. So right now you can see I have it referenced to 000. So when I turn the machine on, it's very important to do a whatever you call it, 0, so that I hit the pins. So right now you see the X and Y position, and it's set up so that if I tap the limit switches, it goes hardware and reads 0. So there you go, X is reading 0. So now if I go ahead and re-reference the system, I'll move the X or the Y carriage, the X carriage, close. And then I can go here and do a ref all home, and I'll choose X and Y. There you go, and well, it's actually reading 1, but that's close enough. I mean, that's within almost 1/150th of a millimeter, so but that is the actual pulse count. So if I probably do another ref all home, it's going to go actually all the way to 0. Well, it's still stuck at 1. That's alright though. The real power here, so I just drove it up and you saw the Y increase. Now I'll increase the X. You see it taking account. Alright, so you can see we have 39,066 pulses on the X and 33,564 on the Y. And I'm going to set that now to a reference of 0. So now I'll drive off of that, and I'll just demonstrate. I can go do a whole series of moves, and it doesn't lose a pulse. Those counters can count at 7 megahertz or 14 megahertz. I can't remember which ones I got, but higher than maximum step rate. So now you can see I'm not at 0, and if I go to 0, goes there, and there we go. We have 3966 and 33564. So it is actually keeping a very, very accurate tally of the position, and this is very important if you want to turn things on and off, because especially with the smooth stepper, the position that these DROs display and the actual position that the machine is at isn't always the same, because they don't it's not a one-to-one live update. So this hardware will work with any system that you have, and it will allow us, eventually I'll be coding this to do PPI kind of laser control, and that will allow us to get the kind of results that we see on the professional Epilogue system, and it only costs about $100 if you don't already have an Arduino Mega and or this board. So it's about $60 for a Mega and $40 for the components to make that board, and it'll be cheaper once I start actually getting a circuit board made. So all I have to do is periodically read the position, and then calculate the distance that it traveled and integrate that, and once it gets to a certain position I can pulse the laser on and off, and there you have it. It's completely hardware controlled, and it's going to work great. This is also probably going to form the basis of an open source laser engraving system. And I've got some other things that I haven't posted about yet that will enable me to use a common CO2 laser and pulse it at megahertz frequencies, and I'll be posting more about that as I have time. Right now it's been kind of a busy time of year. So anyway, hope that's good, and I'll talk to you later.